Hi, it's Paul Bamberg here to introduce you Math156 students to the Bootstrap. When I first saw this idea, I thought it looked absolutely outrageous. Perhaps so will you, but it's one of the modern trends in statistics, and it does a mighty good job under circumstances where you have no idea whatever what the population distribution from what you're drawing your sample might look like. This is based heavily on examples from the textbook, and I'd encourage you to stop right now and read section 5.1 before continuing. Okay, you've read section 5.1, right? So we're going to look at birth rates of babies in North Carolina, and we really don't know the population distribution for this. You can't say, well, the birth weight of a baby is determined by the sum of 1,000 random variables, all with the same distribution, and so the central limit theorem applies. That's just not how babies work. So let's read in the file that contains all these birth weights and extract the weight column as the vector baby weight and plot it. Well, it looks kind of vaguely normal, kind of vaguely symmetrical. We've got 1,009 baby weights here, but suppose we only had a sample of 6. The book actually does this with a sample of only 3. Well, okay, we'll pick 6 at random. Every time you run this script, you get different results. And now we're going to pretend that this is the entire population, kind of as if we took a die and wrote these 6 baby weights on the 6 faces. Can we get any idea of what the sampling distribution might look like? Well, we could certainly say if we had that die, we could roll it over and over again. And what we're going to do is we're going to take all possible ways of selecting 6 babies from this sample. The equivalent of rolling a die 6 times and getting everything up from 6 ones to 6 sixes. And the expand grid does this just beautifully. We're going to end up with a vector or a data frame that has 6 to the 6 rows in it. And if you look down there at the first row, you see what's happened is we've selected the first baby, a rather hefty one, 6 times. In the second row, we selected the second baby, followed by 5 selections of the first baby. The next time we selected the third baby, and then 5 selections of the first baby. And if we went through all the different rows, we would eventually come up with all different ways of selecting babies from this set of 6 at random with replacement. So we can select the same baby more than once. So we're going to work with this as if it were a population data frame. There is the mean for each row, and we can plot a histogram of that. And this is kind of amazing. Out of just 6 numbers, we have come up with something that looks like a fairly reasonable histogram for a sampling distribution. And it's skewed to the left. You might say, yeah, that's reasonable for babies because, I've heard about babies that were 2 or 3 months premature. I've never heard of babies that were born 2 or 3 months after the normal 9-month gestation period. Instead of taking every possible way of selecting 6 babies, we can do 10,000 random samples. That's what we've been doing with permutation tests, for example. So what we do is draw a sample of 6 from sample 6, and key point, replace equals true, because if you say replace equals false and you draw a sample of 6 from 6, you will get back the original sample that you started with. We plot that, and again, it looks kind of reasonable. We can do a comparison with what would happen if we drew random samples from the full sample of 2009 babies. That's what I've done here. I'm sampling from baby weight now. I'm doing my second plot, and it's immediately apparent it's significantly shifted to the left. That's related to the adage, you can't make a silk purse out of a sow's ear. If you have a device that takes a sow's ear and reforms the atoms into a silk purse, it's nonetheless true that your silk purse is going to have exactly the same mass as the sow's ear from which you started. And similarly here, we picked that sample of 6 babies. That's got a certain sample mean. There's nothing we can do to fix that. But what we can try to do is approximate the shape of the distribution. Now, I'm going to do a little gimmick. You might want to use this in your term project. I'm not going to explain the details, but I guarantee if you Google the phrase, "are histogram transparent colors?" you can see how to overlay 2 plots on one another. Now suppose that we take the original data and use very large samples of size 1009. So here are our big samples plotted. And in that case, since we're taking lots and lots of samples from the same distribution, it doesn't make any difference whether or not the distribution of baby weights is normal. The central limit theorem applies. And if we overlay a curve based on the central limit theorem, we'll get the same result. So let's try this out under controlled circumstances. Let's take a population where we know the distribution. We've used this one before. Normal distribution, expectation of 23, variance of 7 squared. We'll draw samples of 50. That's what the density function looks like. There is our expectation right in the middle. And here is a representative sample of 50 obtained using R norm. And there's a histogram of what happens with that sample. The mean is still close to 23, but the distribution doesn't look all that nicely normal. Still, the standard deviation is fairly close to the 7, which was our parameter. Now let's overlay the normal distribution function. Well, the mean matches, the variance sort of matches, but the details are all wrong. Now let's do a bootstrap distribution. So I'm going to do 100,000 samples. I'm running on a fast computer. Don't try this on a slow laptop or you'll sit around for long enough to go off and get dinner. So what I'm doing is taking a sample of 50 from my sample with replacement, replace equals true, computing the mean and storing the result, and I'm making a histogram of that, which, as you can see, matches up beautifully in shape with the normal distribution, except that my histogram is shifted significantly to the left. What does that mean? It means that my sample had a sample mean that was lower than the true parameter. Nothing I can do with bootstrapping will fix that. All I can hope to do is to replicate the shape of the original distribution, which I've done quite well. Furthermore, the variance of the bootstrap distribution comes from the variance of the sample. If I happen to draw a number of samples that are all nearly equal to one another, bootstrapping is going to give me a distribution with a very small variance. So the general rule on bootstrap distributions is you can't fix the mean if you got it wrong, you can't fix the variance if you got it wrong, but apart from that you can hope to replicate the other features of the original distribution, things like skewness and kurtosis. Now we can use this bootstrap distribution, from which we can compute quantiles, to figure out what to add and subtract in order to generate the endpoints of a confidence interval. This is not done in the textbook, and I think it's the right way to do it. I'm using exactly the same technique as before, using the lower quantile to figure out what to add, using the upper quantile to figure out what to subtract. And when I do that, I say I've got a 95% confidence interval for the true mean of this distribution. Now suppose the population is skewed. Let's take a population where we know we've got a skewed distribution, say a gamma distribution that looks like that. This special case of the gamma distribution is in fact just an exponential distribution. Let's draw a sample of 16 from this population. We will get a sample mean that's close to 2. Every time you run the script, it's different, and this is about the largest number I've ever got running this script, 2.5. I expect the variance to be 4. Here I got a substantially larger variance, too. There's a histogram. Since this is a sample of 16, there are big gaps in the histogram, but we can fix that sort of thing by doing a Bootstrap sample. Notice that this histogram really doesn't replicate the density function for the population at all. Okay, let's do our Bootstrap. How do we do that? From this sample of 16, we draw samples of 16 with replacement, meaning we'll pick 16 samples, but we may use some of them twice or 3 times. We may use some of them none at all. And when we plot a histogram, there is a histogram of the sampling distribution, and you say, hey, that does kind of look like the density function for the gamma distribution. From these paltry 16 samples, we have reproduced the skewness. However, when we overlay the original distribution, we see that the two distributions, though similar in shape, are shifted relative to one another. That just means that the sample mean that we happened to get was significantly different, in this case a bit higher than the population mean. Nothing we can do with bootstrapping will fix that. We got the shape right, but the mean wrong. If we think we got the shape right, what we're talking about is the skewness. And if I compute the skewness from the bootstrap, I get 0.09. If by integration I compute the skewness for the original gamma distribution, I get 0.06. So both of these were positive, and they're not too far apart from one another. Now we can use our standard confidence interval technique to figure out what to add and subtract. Here's what we add. Here's what we subtract. And when we use these numbers, we create something that's called a basic bootstrap confidence interval. This is not mentioned in the textbook. You can look it up on the internet if you like. What's mentioned in the textbook is the bootstrap percentile confidence interval, which I think is fundamentally flawed. You can read about that in section 5.3. So, what have we captured? The bootstrap distribution is skewed, and that means that our confidence interval is not going to be centered on the sample mean. Of course, it does make a big difference whether or not our sample of 16 included a lot of samples that came from the tail of the distribution. You might want to run this over and over again and see what you get.